All right, hello everyone, and welcome to my talk, The Zio of the Future. So what I'm going to be presenting today is I'm going to give you a very short description of what Zio is. I'm going to talk about why you would ever want to use a library like Zio. The answer might surprise you. Then I'm going to show you where Zio is headed. And in particular, I'm going to focus on some of the work that a bunch of contributors are doing, myself included, on Zio 2.0, which will be out roughly in the July-August timeframe, a year since the release of 1.0. And then we'll go ahead and wrap up, and I will take questions at the end. So what is Zio? Well, in essence, Zio is a library that helps you build next-generation reactive applications on the JVM. And it consists of the following core pieces. First off, the core of Zio has data types that help you deal with non-blocking and concurrent application development, in addition to building applications that don't leak resources. The STM module helps you build non-blocking concurrent structures with very strong transactional guarantees without having to use locks and condition variables and other low-level constructs like that are prone to deadlocks and, in some cases, race conditions. The streams module helps you build data streaming applications. That could be a socket, that could be file related, it could be a web server, or it could be more traditional data engineering, pulling data in from Kafka and other sources and transforming it and loading it somewhere else. And then finally, the last module is sort of a test kit that helps you very reliably build very fast deterministic tests that don't require any external interaction with databases or other systems. And that part is called Zio Test, but it's basically a test kit for Zio applications. You can learn more at zio.dev, and you can also check out the source code at github.com/Zio. The website there, the microsite at zio.dev, has undergone a huge amount of work recently. So if you took a look at that a few months back and you were thinking a lot of these coming soon pages are never coming, then I encourage you to take another look at that, because there are literally dozens of more pages of documentation than there ever have been, and progress is happening really fast thanks to the great works of a blogger and technical writer, Milad, who's been working on that for some time. All right, why Zio? Why would you ever want to use Zio in your applications? The answer is, you may secretly know that Zio is a library that lets you do pure functional programming in the large. But that's not the answer I'm going to give you for why should you use Zio. The answer for why should you use Zio is use Zio because it gives you superpowers. Using a library like Zio will make you more productive and happier than ever before. It will give you the ability to solve problems that you couldn't solve before, not practically, and you will be able to solve them in way less effort and with a lower cost of maintenance and stronger compile time guarantees than other techniques. That's why you should use Zio. Use Zio if you have very complex applications to build, you want them to work right, you want to have fun solving these problems, and you want to be able to easily maintain them over time. Zio gives you superpowers. Now I'm going to break down some of the more practical reasons into the following buckets: scalability, asynchronous, parallelism, concurrency, resource safety, efficiency, global efficiency, streaming, testability, and resilience. And I'm going to start off by talking about scalability. So if you've been a JVM programmer for a while, you know that the JVM exposes this construct called the thread that lets you do multi-threaded programming. Multi-threaded programming is important because it's how you do not just concurrency, but parallelism. It's how you get more stuff done in a smaller amount of time. It's how you improve or reduce application latency. You can cut down the amount of time it takes to process requests. You can shorten the amount of time it takes to crunch numbers or do analytics. You do all of that by taking advantage of all the resources on your computer. And those resources come in the form of threads. So the JVM has a construct that helps you do that, and it is called a thread. Well, Jvm Threads, an early decision way back in the dawn of Java, was to map JVM level threads to operating system level threads. And that decision way back at the dawn of Java has had very profound implications for the evolution of the programming language, as well as the libraries that populate all the JVM programming languages. And one of them is that a lot of JVM-based applications have run into scalability problems because threads don't scale very well. Threads are actually very heavyweight, bulky structures that slow down your application. And you can't have too many of these threads running at once in your application before you get overwhelmed by the amount of overhead in every single thread. Some of the reasons why this is the case are that every single thread in your application has a pre-allocated stack that consumes a certain amount of memory. It's allocated when you create the thread, it's pre-allocated, and it's sucking up memory all the time, whether or not that thread is actually using all of that memory. In addition, threads are explicitly started and they must be explicitly stopped. That is to say, a thread that is doing activity will continue to run and continue to take up resources until that thread is terminated. It has to be interrupted, it has to be shut down, or it has to end life normally. Otherwise, it continues to take up all these resources. In addition, every thread on the JVM acts as a new route for garbage collection analysis. So when your JVM is trying to figure out all the bits of memory that are not used in your application, it's got to look for all the live threads because all the live threads have their own unique references. And so that slows your application down. And then finally, the more threads that you have running in your system, the more time you spend doing something called context switching. This is when your hardware switches over from doing the work of one thread to doing the work of a different thread over here. It's got to do that because you have more threads than the number of cores on your machine. If you have 100 threads and 4 cores, then you've got to divide all 100 threads by the 4 physical cores on that machine. And so you have to have these individual cores switching around a lot, jumping back and forth. And there's a certain amount of overhead that has to happen. You have to swap in the registers and all the other stuff. You have to go back and forth. That takes up time. As a result of all of these limitations, what has happened is there's something called the 10K limit. The 10K is roughly the maximum number of threads that you can have in a modern application before the overhead of the threading machinery starts to dominate your runtime. You can't scale past 10,000 threads. And that's a very lower bound. I mean, that's not a very high bound, upper bound on the total number of things that you can have happening in a modern web server. Because if you're serving, millions or tens of millions of users, then you've got potentially lots of, for example, web connections all up and running at the same time, even though very little of them are doing anything at one point in time because you're using a lot of them for notifications and other sorts of very long dormant period activities. Nonetheless, you've got all of them open. That just doesn't work. It doesn't work with threads. So what Zio does is it comes along and gives you a different story for scalability. Instead of exposing the notion of a JVM thread to you, it exposes the notion of a Zeo Fiber. And a Zeo Fiber is essentially a virtual thread. It is a virtual thread before Loom arrives. So Loom will eventually bring true virtual threads to the JVM, but that's going to take 5 years or so and even more time for all the libraries to catch up and for people to upgrade to the latest JVM version that supports these features. Until then, you have Zeo Fibers. And Zeo Fibers are very lightweight, sort of green threads implemented at the library level. And whereas every single JVM thread maps to one operating system thread, you can have hundreds or thousands of Zeo Fibers all being mapped to a single JVM thread. And unlike a JVM thread, an operating system level thread, fibers have tremendous benefits. For example, fibers that are not doing active work and which can never ever do active work because no one can wake them up again are automatically garbage collected. That means in many cases, you don't have to worry about explicitly shutting down fibers because if they're not doing active work and no one can reactivate them, no one can wake them up in some fashion, then the JVM will take care of shutting them down for you, including garbage collecting all of the memory that they are allocating. In addition, fibers, unlike actual JVM threads, have dynamic stacks. So their stack size starts out really small and it can grow over time as the fiber needs. And then when the fiber doesn't need all that memory, the stack can shrink back down again. So they're not pre-allocated. They start off essentially 0 and they go up and down based on the requirements of the application. Fibers do not add new GC routes, so they simplify the garbage collection process. And there's less context switching involved with fibers than with threads, because when a fiber is not doing active work, it no longer needs to hog the CPU, and there never needs to be that context switch. It can voluntarily yield when it's not doing active work to some other fiber that needs the CPU. And then later on, when it's reactivated, whatever CPU was executing that can sort of voluntarily take on doing the work of that particular fiber. So you end up with significantly less context switching, which is a form of overhead that ends up dominating highly multi-threaded applications. As a result, while the boundary, the sort of upper cap on the number of productive threads you can have in an application is 10,000, you can easily have an application with 100,000 or even in some cases 1 million fibers. They give you the ability to scale to heights never before seen on the JVM. That's what fibers give you. And Zio, it was the first library to support fibers in the Scala programming language, and it has very excellent support for them. Another compelling reason to use a library like Zio is that you never have to deal with callbacks ever again. So callbacks, there are still libraries out there that require you pass in a function and it will call you at some point. Lots of low-level libraries like Netty and so forth, they still have these low-level callback-like constructs. The listeners, anytime you see a listener, that's a callback in disguise. Listeners are not easy to work with. They're super hard. Callbacks are very difficult to work with because of the amount of nesting that happens. And every time you start using callback or listener-based API, you lose a lot of the nice properties of the host language. For example, you lose the ability to do try finally. You lose the ability to catch exceptions. All of the ordinary machinery in your programming language breaks down when you start going to callbacks and listeners and async non-blocking style APIs. Well, Zio, what it lets you do is take a legacy callback API and refactor it into something that is 100% non-blocking. So it's every bit as non-blocking as the old callback-based API with listeners. However, it is semantically blocking. And that means from your point of view, using that API, it looks like this is happening, and then you're waiting, and then it's going to continue on and do this, and then that's going to happen, and then it's going to continue on and do the next thing. And then Zio gives you facilities to recapture the things that you lose when you use callback and listener-based APIs. For example, you have try finally again. It's not called finally in Zio, it's called ensuring, but you have it. And it works with synchronous or asynchronous code. And you have the ability to catch exceptions. Unlike with listener-based APIs, where exceptions will often get lost, you have the ability to catch them with Zio. It gives you all of the tools that you know and love from your host programming language, but in a package that works with async non-blocking code, and that saves you from having to ever see a callback or listener-based API again. You can work at the level of semantic blocking. We're going to do this, do this, do this, and do this, and you never have to worry about messy implementation details, such as, is this implemented with callbacks or is it implemented with synchronous code? In addition, Zio gives you extraordinarily powerful tools necessary to maximize parallelism in your application. So in many cases, parallelism is baked into the web framework you're using, but if you're writing more specialized code, or if you have ultra low latency requirements, then it makes sense to take advantage of parallelism. You have lots of cores, and not only do you have lots of cores, but a lot of activity. If it's built on NIO or other sort of next level non-blocking IO systems, then that means it's not necessarily going to block. You can afford to initiate multiple of those requests at the same time, and you'll actually end up reducing latency. Zio gives you that ability. For example, every single operator in Zio that can have a parallel version does have a parallel version. And not only does it have a parallel version, but it has a parallel version that lets you cap the amount of concurrency in that operation. So Zio gives you for each, so you can for each over a list or something and perform effects for everything inside that list and then collect all the results back together again. And because that operation can support a parallel version, you have it, and it's called for each par. And not only you have for each par, but you have another version, for each par n, that allows you to cap the concurrency. So if you have a list of a million things, you're not trying to do a million things in parallel, which doesn't make sense. You're only trying to do a specified n number of those things in parallel. In addition, Zio has tremendously powerful capabilities for writing concurrent code. It has, I believe it has the most sophisticated concurrency system in Scala and maybe even in the whole JVM. Just the number of things, the number of tools it gives you and the power of the guarantees that it gives you behind all of these concurrent operations are second to none. In this little example snippet of code here you see on the screen, what happens is we take one thing from a queue and then we perform work on that. We do that forever in a loop. And that gives us this thing that I call a worker. We take that worker and we fill a list with n of them. So now we have n workers, and then we fork all of those workers. And now we get back a single fiber basically that is doing the work of n workers all pulling from the queue. So we're doing a tremendous amount here in a small amount of code. And we're writing code here that is automatically safe and it can be canceled and all of the other great properties that Zio gives you that they hold up under the presence of composition like this. In this snippet of code, we're using something even more advanced in Zio called STM. And STM actually gives you transactions. It gives you database style transactions on memory on a local computer node. And the benefit of that is that because the type of transactional support that it gives you is capable of waiting for conditions to be met, you can wait for this to happen or wait for this to happen and only commit the transaction when those conditions are satisfied. This mechanism wholly subsumes 100% of what you would use Java util concurrent locks and condition variables for. This means that you can solve all problems that you would ever reach into Java util concurrent for, but you can solve it in a way that's compositional. So that means that locks don't compose. You can't lock this and just do both things. You're going to run into deadlocks because locks are sensitive to order of acquisition. Locks don't compose. Code that's built on locks don't compose. If you suddenly decide you need to change two things at once, you have to re-engineer the whole part of the code. It's not like you can say, oh, we just need to, modify this as well as this. No, you have to re-engineer the whole code. Whereas the transactions that STM gives you are 100% composable. In addition, because they are composable, you never run into the deadlocks associated with lock-based systems. And also the complexity of waiting to commit a transaction in memory until certain conditions are satisfied is totally hidden from you. There is no concept of a condition variable with STM. You just say what you want to wait until it happens, and the STM system will wait until that condition is satisfied before it continues with the transaction. So in this case here, we look for a connection that's available. We're building a little sort of acquire a connection from a pool. We actually just look until that connection is available, and then when it's available, we take it off the available list and we add it to the use list, and then we commit that atomically. And we don't have to worry about race conditions because everything inside that atomically block happens with transactional guarantees. And that get collect that you see there is actually going to wait until there is a head element on the list. And when there's not a head element on the list, that transaction will be suspended until there is one. So it totally and elegantly, beautifully eliminates all of the complexities of concurrent coding and makes it so that ordinary programmers who don't have PhDs in semaphores and other very advanced concurrency control mechanisms and all the lock support and unsafe park, all that stuff that is baked into Java util concurrent. If you don't have any of that, but you have to do something that is related to concurrency, you can easily do that with STM. Zio also provides very powerful abilities to totally eliminate all sorts of resource leaks in your application. And there's no better example of that than Zio than the managed data type. So the managed data type, what it lets you do is bundle the acquisition of a resource with its release. You do that by calling managed make. You provide the way to acquire the resource and the way to release it. You bundle that up into managed, and now you can use managed. You can combine managed with other managed, and you can transform one managed into another one. You can map over those things. You can compose them together using all the operators that you know and love from Zeo. And you have the guarantee that no matter what you do, you will not leak resources. That's tremendous because it means you can open files, you can acquire connections from a database pool, you can acquire remote resources from a server, you can, like even virtual resources, like we're only going to allow 100 connections at the server at the same time. You can do all of that in a way that's bulletproof. You will never leak any resources under any circumstances, and it doesn't matter what sorts of crazy compositions or timeouts or cancellations or whatever you have going on, you still have these bulletproof guarantees that you're never going to be leaking any resources. And you just can't achieve that. In modern applications that are hybrid of sync code and async code with listeners and callback-based APIs, and you've got acquisition over here and release way over here, and any number of things could go wrong. Now, there's no connecting those 2 points of code. You can't make guarantees like that. In fact, that's one of the main reasons why these sort of application frameworks are so insanely valuable, is they allow us to take our poorly written leaky code and restart applications on a regular basis because we know they're leaky. We just don't want to take the time to actually fix them. Well, Zeo gives you the machinery you need to make sure you build applications that never, ever leak, no matter what happens. Zeo also has this property in it that it's automatically globally efficient. Unlike Future, for example, where when you're done with the Future and you don't need it anymore, it continues to run in the background indefinitely until it's done. That could be 2 hours later or 2 days later, resulting in massive thread leaks, as well as slow application performance and memory leaks and all sorts of other problems. Zeo is globally efficient. This is something that you could, in theory, achieve if you were to write all this code by hand and to manually check for cancellation and to cancel all your loops and to cancel all your socket connections and all the other sorts of things that you would have to do if you wanted to achieve this. But the amount of work involved in doing that in a real application would be so tremendous, no one would ever attempt that. As a result, Zeo gives you the ability to be globally efficient in a way that's simply not practical for any other class of application. An example of this is a race. So anytime you race to a fax and you want to get back the first one, then the loser of that race will be instantaneously canceled in a way that's still safe. So if that side acquired resources and it's canceled, then those resources will be released in the process of cancellation and wind down of that effect. In addition, anytime you time out an effect in Zeo, if that time elapses and that effect has not completed by that sort of measure, then that effect will be canceled right away. And again, all resources that it acquired will be safely released. So this means that in large applications that have hundreds of requests, they have tons of things going on, when any part of this global sort of application dependency graph is not needed, it just goes away. All resources associated with that are released, and your application continues humming along without wasting CPU on memory on computations that would never be needed. And these lead to real, measurable, hugely measurable impact. If you compare Zeo-based applications with Future-based applications, it's enormous. In fact, Future-based applications can be so inefficient that people go and build their own futures or their own cancellation mechanism because they can't afford to pay for the costs of running all of these threads and consuming all this memory that's never going to be used. Imagine when, like, even the mere act of canceling the socket connection request because the browser decided it's going to do something else, you can't afford to continue running all the database queries and the Redis queries and all of the stuff that's going to be happening if you can't cancel that. Well, you get all this cancellation stuff for free everywhere, pervasively across your entire Zeo application without having to lift a finger. Zeo also has tremendously powerful streaming capabilities that allow you to work on infinite streams in a concurrent fashion in a finite amount of memory without leaking resources. So Zeo streams are concurrent and resource safe by default, and they give you the different capabilities you need. In any streaming library, you need, at minimum, two things: a stream and a sink. They're duals. In the category theory sense of the word, they're duals. Streams are producers of values and sinks are consumers of values. and you connect them to form a full pipeline. And so streams in Zeo, they produce values, sinks, they consume them. Both of them are resource safe. Both of them are concurrent. They complement each other perfectly. Zeo gives you those two tools necessary to solve all problems in the class of streaming data applications that you might ever need to solve. Zeo also has built-in first-class ability for you to test anything anywhere. And it achieves this through use of Zeo environment and following object-oriented best practices like code to the interface, not to the implementation. It gives you the ability to create fast-running deterministic tests, even if your code is interacting with consoles or databases or system time, even if it's sleeping. All of that can be done, can be tested in a deterministic fast fashion that does not involve any interaction with the outside world. And Zeo's test kit, the Zeo test library that ships with Zeo, provides extraordinarily powerful and compact means of making sure that the modern async, concurrent, resource-safe code that you're building is 100% ready to go into production by satisfying all of these unit tests that you've written. And then finally, the last reason why Zeo, well, not the last, I have one sort of surprise reason at the end, is resiliency. Our applications need to run. They need to deal with failures. They need to deal with external failures. So when databases are down, APIs are down, those types of things, we need to be able to deal with transient failures. And Zeo has compositional schedules and retry and repeat and schedule operators that allow you to handle any sort of failure scenario that might possibly arise according to whatever your needs might be, whether it's exponential fall off, cap, limited, all those scenarios and infinitely many more are supported using a compositional type-safe API that can be tested deterministically and instantly in a unit test without actually waiting for any period of time to elapse. And not only does Zeo give you the tools necessary to handle external failures, but the other type of failure that we need to be able to handle in order to build resilient applications is internal failure. And Zeo has, as Girish mentioned earlier, Zeo has typed errors. It has a typed error channel. What that means is that just like the typed success channel, so future of A, that A is your typed success value. And that lets you reason about success. It lets you reason about, oh, this produces this, and that value goes here, and so forth. So Zeo takes that concept of typed success and says, well, why don't we use that for failure channel as well? Why does the success channel get to have all the fun? Shouldn't the failure channel have just as much fun? And so Zeo mirrors it and says, okay, now you have success and failure channels. And you can see that when you're looking in your IDE, you can see, oh, this bit of code, it fails with an IO exception. I better handle that. And then when you handle that using catch-all, you can see, oh, in your IDE, you've handled that error. This code can't fail anymore. So you can actually see in all parts of your application whether things can fail or not, and if they can fail, how they can fail. And that's just amazing. It's amazing because it allows you to understand before you run your code what the error handling behavior will be. And once you've gotten used to this feature, you can't understand ordinary future-based code anymore. You're like, I have no idea if this is going to succeed. Maybe it does. I have no idea if this error was handled. I don't know if this can fail. I don't know if it can fail in these 2 ways or 100 different ways. There's just no information that the Scala compiler gives you with future. And with Zeo, the Scala compiler gives you everything. It gives you the ability to understand exactly where and how all parts of your application will fail. And that leads to bulletproof applications that perform according to specification without you even having to run it. You know that in advance at compile time, which is amazing. It's just eye-opening if you've never used that before. And then the bonus for why Zeo that I want to give you now is not only do you have all these great features, but even better, all of these features compose together. And what that means is not only can you use them in isolation and have their strong guarantees, but you can start mixing and matching them. You can put them together like Lego building blocks, and you can solve insanely complicated problems in a way that has no edge cases. it functions as specified, as you imagine, as you think that it should function, without any sort of edge cases, no matter how much complexity you're taking on. And that's a property unique to functional coding. Good functional design lets you solve problems in a compositional fashion, which means it doesn't matter how complicated the problem is, you can break it down into those building blocks, each of which is principled and well-reasoned. If you understand the pieces, you can understand how the solution fits together. Let me give you an example of that. Let's say we are tasked with opening up a file, some sort of resource that contains a lot of information, and using the contents of that file to search for something. So we do some sort of breadth first search on the data that's inside that file. We don't want to leak resources, right? So we use managed. And we say, here's how you acquire it, here's how you release it. We bundle that up into managed, and now we don't have to worry about resource safety. And the code that uses that resource can be physically separated from the code that makes it, which is nice because code that uses a resource should not necessarily have to know or concern itself with how to acquire and release it. That's a principle of modularity that managed makes it possible to take advantage of. So this is the solution. Nice, simple, straightforward. But what if our manager comes to us and says, we need to support multiple URLs. It's not enough to just do it with one URL. We need to do it with many URLs. So what do? Well, we put in Zeo for each, and we nest that code in there. And now we do the same thing for every single URL in this list. That's it. And Zeo for each will apply that logic again and again and again for every URL inside there, and it will collect together all the results in a compositional fashion. But what if our boss comes back to us and says, no, this is not enough. This is too slow. We need to load the data in parallel. It's not enough to do this sequentially, one after the other. We need the whole thing to be in parallel. And so we go and we make a change. We change for each into for each par. And then suddenly all of this stuff is loaded in parallel. Amazing, you know? We changed 3 characters in order to satisfy that business requirement. And then our boss comes back to us and says, no, that's too much parallelism. There was 100,000 URLs in there and you're doing all of that in parallel? No, limit parallelism to 20, you know, at most 20-way parallelism. Well, we add another character for, for each par n instead of for each par, and then we specify 20 parallelism number, done. And then our boss comes back to us and says, no, because sometimes when you open up these URLs, the act of opening that connection, it fails. And we don't want to fail the whole process just because one of these URLs was a little flaky. Let's retry the opening up of this. And so what do? Well, we call .retry on that managed resource, and we specify a policy, in this case, a policy that just recurs 100 times. So we'll retry connecting to that URL up to 100 times before we give up. The overall structure of our code didn't change almost at all. We just added more stuff. Notice at every single step, even though the requirements keep on changing, we don't have to rewrite the code. That's astounding, because if you solve these types of problems in a non-compositional problem, one requirement comes in like that, and you have to rewrite the whole thing. That's what happens with actors, is one little requirement comes along, and boom, it's a totally new design for that system. And not just with actors, by the way, that's a general purpose problem. And any system that's not compositional, you have that problem. Compositional systems have the following property. Business comes in and says, change this thing in this way, and you go into the code and you literally, you fit together 2 other pieces, or you add this unary operator on top of this value to produce a tweak value, and then problem solved. The maintainability of functional systems is extraordinarily high because small change in business requirements means small change that is refactoring friendly inside the code that's constructing the solution. That's an amazing sort of game-changing feature of functional programming, is the ability to maintain systems cheaply. So let's say our boss comes back and says, no, that's not enough. It's not enough to try 100 times in a row. We need exponential backoff because we've got too many of these systems sort of hitting at the same time. So how do we do that? Well, we add something new. We add exponential schedule into the other schedule. So we do schedule intersection here using that and operator, and boom, now we have 100 retries. but they'll all be spaced according to an exponential schedule. And the boss says, no, that's not enough. We need to time out the retry, because if this retrying takes too long, we want to give up. And so we just add timeout fail and we add 30 seconds. And then finally, not finally, almost finally, our boss says, we don't want to necessarily search breadth first, because we know in some cases it's going to be faster to do a depth first search of this data to find what we're looking for. So we just race the two together. We race the breadth first search with the depth first search, and then whichever one is the loser will be canceled. We don't have to worry about resources. We don't have to worry about interrupting that computation. All of that happens for us. And then finally, our boss says, come time out the entire thing. So if the entire thing takes too long, we want to shut down everything. And keep in mind that shutting down everything potentially involves terminating all of these 20 parallel branches that are operating. Some of them are in the process of opening resources. Others are in the process of closing. Some of them are currently using their resources. The ones that are using their resources could be involved in a simultaneous concurrent breadth first search and depth first search. And some of these things could be timing out. We don't have to worry about any of that. All we have to do is add dot timeout 10 minutes. And the rest of that is taken care of for us. That is the power of composition. And that's why I say using Zeo will give you superpowers, because you can't write code like this. You can't write code that solves this problem by hand. It's not possible. You need composition. You need functional programming to give you this much power. And that's exactly what Zeo gives you, is the ability to solve insanely complicated problems with just a few lines of typing. It really does it gives you superpowers. And it's fun. It's fun to write code like this because you can understand it. You can test it. You can change it. It doesn't matter what changing requirements they throw at you. You've got it covered. You are in control. You are in the driver's seat. When you use a library like Zeo, you are in control. Compositionality, that is the key. That is what makes functional programming so great. Compositionality. I cannot say that enough. It's, yes, the static types, all of that's wonderful, but it's the compositionality that I just showed you, that I just demoed, that really blow my mind and the minds of people who have been doing FP for quite some time. And finally, I would say the last reason to use Zeo in particular, because if you're sold on a functional effect system, and I hope this presentation has done that for you, then you still have some choices. Why Zeo in particular? I would say Zeo has been at the forefront of innovation. It has been responsible for so many firsts. For example, first fiber-based concurrency system, first system to have safe, pure auto cancellation. The Zeo model was replicated elsewhere. First system to have statically typed errors, lossless error model, context propagation, principal thread shifting, async execution tracing, fiber dumps with await detection, industrial strength STM, on and on and on and on. Zeo has been first in all of these categories. And this is just where we are today, let alone where we're going with Zeo 2.0, and I'll get to that momentarily. So where is Zeo going? Well, Zeo is taking things to a level never seen before in any open source Scala ecosystem. I really believe that. I'll give you a few reasons. Some of you have attended Zeo World and already know, but for those of you who have attended Zeo World, I have a few surprises at the end. So sneak peeks of things coming to Zeo 2.0 that we've never talked about before, that we are talking about today for the first time. And by the way, before I begin the section, I just want to thank all of the numerous contributors who are involved in making Zeo 2.0 a reality, including Itamar and Adam and Dayon and Rob, Maxim and Kit, and so many others who have pushed this forward and gotten it to the point where it is today. So Zeo is a rapidly growing open source project. We are up to 1 million downloads a month right now, and these numbers continue to grow. And all that from a project that's been around for, at least it's been 1.0 for less than a year. It's amazing to see that kind of growth. It has tremendous commercial adoption. So all the companies you see on this slide here are using Zeo in production, and many other ones as well. Actually, we know some of the ones that are using it They just haven't made it up here. I haven't updated this slide, but there are more. And then there are some that we can't talk about for NDA reasons that are using it. And then there's probably dozens or who knows how many exactly who are using Zio who just haven't told us about it, and they're just happily using Zio in quiet. So what we've done in Zio 2.0 is we've added polish, tremendous amounts of polish. So Zio 2.0 is not brand new. It's not going to require a rewrite of your code. Barely anything changes from the surface level API. It's proven in production. It's working extraordinarily well. Zio 2.0 is primarily about adding a few things that were missing and adding polish in areas that were not as smooth as we would like them to be. And polish, one aspect of polish is improving performance. We don't want any company to say, we can't do functional programming because it's too slow. In fact, I want companies to say we have to do functional programming because it's faster than what we're doing today. I would love it if all companies said that. And so we need to spend time making sure that the engines that power Zio and all the features in Zio are as fast as humanly possible. And so some of the work I've personally been involved with involves improving the performance of Zio's runtime system. Zio's runtime system already has a very fast design that's been hardened and converged on with sort of numerous changes over the years, all the way up until the point where we got 1.0 ready to go. But I've invested additional effort in making sure that it's as fast as it can be. And you can see collection operators are significantly faster than Cats Effect 3 in almost all benchmarks. Region-based operators, so a lot of the heavy-duty lifting in Zio uses operators like uninterruptible or ensuring, that's Zio's version of finally, uninterruptible mask, which gives you fine-grained control over cancellation, bracket, which gives you the ability to pair and acquire with a release. It powers managed and other things. These are operators that are very complex. They're very complex because if anything goes wrong, you have to undo whatever you did. So they're region-based operators. Making them super fast is difficult. And I've invested a lot of effort in Zio 2.0 in making these super fast, and I think the results speak for themselves. In addition, one of the things that Girish mentioned in his presentation is that you can and must, in fact, in many cases, reuse Java libraries and Scala libraries. You should be able to do that, and you should be able to do it without performance penalty. And so in order to help make that possible, I've invested a lot of effort in making sure that whenever you have to take a Zio effect and run it, and you have to do that many times in interop, because sometimes you'll want Java code to call into your Zio code, and it doesn't know about effects, so it actually has to run them. If you make a callback calling to Zio, it has to actually execute that effect. I've invested a lot of effort in making that really, really fast, which is key if you want a functional effect system to be practical. Because to be practical, you've got to be able to use all the existing libraries out there to be able to use them without significant performance penalty. And you can see here that just the order of magnitude, how much faster Zio 2.0 is than, for example, Cats Effect 3 is just tremendous. Opening up the doors to more or less, you don't even have to think about interop anymore. If you need to unsafe run something, you just do it, and it's super fast. Iteration is a big priority in 2.0, making the iteration operators, both the sequential versions and the parallel versions, really fast. And so a ton of effort's gone into optimizing those. In addition, one of the areas where fiber-based effect systems can innovate, and where Zio 2.0 is innovating, thanks to the work of Adam Fraser, is in a scheduler that is fiber aware. So a scheduler is what sits between all the fibers and says, okay, you fiber, you're going to execute on that thread. And then you fiber over here, you're going to queue up behind that other fiber and wait your turn in line. And that fiber over here is going to execute on this other thread and so forth. A scheduler is responsible for taking those million fibers and deciding how they get executed on 4 threads. That's a hard problem. And in Zio 1.0, we actually used something that's built into Java to perform that work for us. However, that doesn't really take advantage of all that we know about fibers. And so, building on some work that was done in the Rust open source community, Adam has created a scheduler that knows about fibers and takes advantage of the peculiarities of non-blocking fiber-based effect systems like this, and optimizes the way in which all of these fibers are mapped down to the physical threads that end up executing their logic. And the results are tremendous. Basically, improvement over Zio 1.0 is quite significant. If we measure purely synthetic benchmarks, Zio 2.0 scheduler is way faster than the Zio 1.0 scheduler. And it's also faster. Cat's Effect 3 also has a fiber-aware scheduler, and the Zio 2.0 scheduler is faster in all of our benchmarks than the Cat's Effect 3 scheduler. One area where we've known for a while that we needed to improve was layers. So layers are frequently cited as the one area of Zio that's not so fun, and that really confuses a lot of people who are new to the library. So we've heard all of your criticism. Thank you, by the way, for that. Criticism is always good because there's always some truth in every bit of criticism. And one of the things that us contributors are trying to do is be open to that and just say, yeah, if you have feedback, tell us. Even if we don't want to hear it, we do want to hear it. We especially want to hear the stuff we don't want to hear, because that type of feedback is how we make the library better. And so we've spent an enormous amount of time trying to figure out how to make layers simpler. Layers are what enable you to dynamically wire up an application dependency graph, as well as to carry context to different part of your applications. They make it easier to code to an interface instead of an implementation, thereby facilitating higher testability. So that's what they do. That's what layers do, is they facilitate testability. And there were several problems with layers in Zio 1.0. One is we encourage people to use this module pattern that actually was quite confusing, especially for developers coming from Java. The module pattern involved a package object that contained a type alias that pointed to a service trait in a companion object, and it was just all very weird. And then there was accessors and other things. So this has been radically simplified for Zio 2.0. We're starting to teach module pattern 2.0, and this is way simpler and also much more familiar to Java developers. So we're just teaching, make your classes case classes, okay? So every time you create an implementation of some component, make it a case class. And of course, obviously, if you want, you can have an interface as well. You don't have to have an interface. In some cases, you might choose not to, but you could have an interface, and then you could have a class that implements that interface. And then your class that implements the interface is going to take as its constructor parameters any interfaces that it depends on. So classic constructor-based dependency injection. We're not trying to change that. We're not trying to change anything you're already doing inside your Java applications. If you're using Juice, you're already used to this pattern. One class takes in its constructor parameters interfaces that represent all the dependencies that this implementation of a service has on other services. So don't change that. Do the same thing. The only little tiny difference with that is inside the companion object of that interface or the class, if you're not using an interface, you're going to put a layer. And that layer is just a wrapper over your constructor. In fact, for simple constructors like this user repository, all you have to do is call toLayer on it, and that's it. That's all you have to do. Then the process by which you can access that user repository in your Zio code is way simpler as well. You can use this thing called service with. There's no type alias, and you just directly inside the Zio environment, you will mention which services you're accessing by using the has wrapper. So you'll say has user repository with has logging, with has config, and so forth. So this is a significant simplification, and early results seem to indicate that this is substantially easier to teach and easier for new developers, especially new developers to functional Scala or to Scala itself, to pick up on. In addition, we're simplifying the construction of more complicated layers. So for simple layers, all you have to do is take that constructor and call toLayer on it. For more complicated constructors, we're basically deprecating all 5 billion methods inside ZLayer. That was one of the confusing parts about ZLayer, is the companion object had about 5 billion methods. And you never know which of those 5 billion you have to call in this particular case. Not even I know. And I wrote a good chunk of them, if not all of them. So what we're going to do in Zio 2.0 is delete almost all of them. Instead, we're favoring a very simple pattern that maybe it takes a little bit more code in some cases, but it's super uniform. You can use this pattern to construct any layer you want. It's very simple, it's very regular, it's very easy to teach. And what it is in a for comprehension, you just place all of the services that your layer needs. So for example, you need database and you need logging and you need config. So you just pull them all out using zio.service in the for comprehension, and you pass them as arguments to your constructor. That's it. And then once you do that in your for comprehension, you call toLayer on it. If you need things like refs or whatever other things you need to feed into that constructor, you just create them in the for comprehension. It's simple. The type inference works out great. You don't have to write types out here except for which services you're picking out of the environment. So it works great. And also it scales up. So if you have a layer that needs to allocate and deallocate things, then you just do everything in zmanaged. So you call zmanaged.service and you just convert things to managed, and then you can use managed things like connections and files and sockets and things from pools, connection pools and other types of things. You can use all of those resourceful things in building up your layer. It's the same pattern. It works the same as the other one. It's just the resourceful version of that pattern. So these two different patterns, the sort of Zio simple pattern and the Z managed more complicated pattern, are wholly enough to build any possible layer you can imagine. Then another great bit of work that Kit has done is he has implemented support for automatically constructing layers from their individual pieces. So previously, if you wanted to build a complex layer that required a bunch of things, and those things required a bunch of things, and so on and so forth, you had to wire that up by hand by using arrow composition operators. And if there's one thing that I now know about the Scala programming community and even the functional programming community, is that no one knows how to compose arrows. No one knows anything about arrow composition, and it's very confusing. And not only that, but the error message that you get back if you make a mistake are quite complicated. And tools, even like IntelliJ IDEA, they don't have great facilities to tell you what you did wrong. So people have to do crazy things like take type errors and try to diff them in order to figure out exactly what went wrong, the difference between expected type and the actual type. And that's just crazy, of course. So in Zio 2.0, Kit's work has enabled us to automatically build the application dependency graph from its individual pieces. And in fact, if you don't supply something, you get back a super helpful message, as well as a graph showing you, oh, you're missing this one. You need to provide this one over here. And this revolutionizes the usability for layers. It moves it from something that requires a lot of time and effort to explain and teach and results in a lot of frustration as you use it. Even if you're an advanced user like me, some of the type errors that I got back, I'm like, that's too much work to figure out how to understand. I'm just gonna, try more precise types and solve it that way. It turns it from that painful situation that's hard to teach into one that's so easy. Someone brand new to all of this can be successful immediately without any training. That's the difference. It's night and day difference in usability. It's revolutionary for the usability of layers, and I think their adoption. Not everyone uses the environment in Zio 1.0, and part of the reason is layers are too complicated. In Zio 2.0, I think 90% of people will be using layers. In addition, Kit's implemented this really great way to auto-wire a layer, which is just constructed automatically from all of its pieces, so you can use that layer across many different areas of your application. So you don't necessarily just have to provide your effects with everything they need right there. You can bundle all that up into a layer, which then you can provide a bunch of different times in a bunch of different parts of your application. I think the other one is, this one works really nice for sort of demos and getting people started. In big applications, you'll want to use this one because you want to put those layers and values that you can reuse and share across parts of your application. And again, if you get anything wrong, the error messages are amazing. Another thing we're doing in Zio 2.0 is we're trying to improve ergonomics, and that means simplification. It means deleting multiple ways to do something, and it means making sure that names of operators are reflecting their purpose in a given domain rather than reflecting something from functional programming or category theory or Haskell. An example of the former, which is removing multiple ways to do something, is right now you can call Zio effect total or Zio succeed, and they have the same effect. So why do we have both of them? Well, in Zio 2.0, we're not going to have both of them. There's just going to be Zio succeed. So you'll be able to call Zio succeed with some sort of side effect, some interaction with the external world, like print line, like you can do today, and that will be the encouraged pattern. If you know that to succeed, well, that's basically what we mean by effect total, because you're saying, oh, it's going to succeed. So rather than have both of them that do exactly, literally exactly the same thing, but with different names, we're going to delete one of them and make Zio simpler, remove choices. There should be fewer choices, become more opinionated, and say no, and just always use Zio succeed. In addition, Zio.effect, that is not very descriptive. Of course, it's precise in an FP sense because we're saying here's a side effect that we're converting to a functional effect, but that's the theory. What does the practice say? Well, the practice is more like we want to attempt something that might fail. So instead of calling it Zio.effect, we'll call it Zio.attempt because we're attempting something like reading a file that might actually end up failing. And then other miscellaneous simplifications, not too many of these, but in general, we want to delete things that are redundant, and we want to give a few better names to common operators that had more FP-inspired names. But now, sort of through time and practice, we see the value of naming things according to a domain and according to their purpose, rather than according to FP jargon. So another amazing thing that's coming, baked into Zio 2.0, is the ability to profile your Zio applications. Why is that so amazing? When all you've probably heard about JProfiler or YourKit or Visual VM. It's amazing because if you've ever used a traditional profiling tool on a Zio application or a future application or any of these other effect systems, you'll find out those profilers, they don't tell you anything useful. And that's because when you sit there staring at all the lines of code that suck up your application execution time, they're all in Zio. They're all in the Zio run loop. You learn about how much time your application spends in the run loop, which is basically all the time in the world. It spends the whole application in the Zio run loop. Well, that's not going to tell you what to optimize. It's useless. So thanks to the work of Maxim and Dayon, Zio is getting a built-in profiler. All you have to do, it's literally this easy to set this profiler up in your application code. You just say what you want to profile, and then you get back the data from that, and then you choose to write it to some sort of file, and then you can open that file in a tool to see the actual impact. The method here used to implement this profiler is called Causal Profiling, and it's a relatively new technique for profiling applications that works extremely well for async code, and in particular, it works very well for Zio because Zio already has, or almost had, and now with Zio 2.0, it has everything necessary to place the right hook into the runtime system necessary to peek in and to see. How this method works is that it basically goes through all the lines in your application, which Zio knows about, because Zio has execution tracing. It knows where all these different bits of code came from in your own application, and it slows down different lines of code basically, and that is basically equivalent to speeding up other lines of code. So, and then it measures the total amount of time spent executing that, and it sees basically if we slow down this line of code, it had no effect on the output, the runtime. If we slow down this line of code, it had a massive effect. So clearly this is the one where we need to optimize. So it analyzes, it finds performance bottlenecks in that fashion. It's really amazing, and it actually gives you very useful information. So you profile a bunch of Zio code, and now this will tell you, you have a hotspot here, you need to optimize this one. You have a hotspot over here, you need to optimize that one. And it can direct you right to those performance problems. Something Rob has been working on is improving our support for execution tracing. So Zio was the first effect system to ship with execution tracing. It actually shows you your execution trace as you're going along, leading up to a point of failure. And then it shows you a stack trace, but that stack trace is asynchronous, so it's async friendly. And that was a game changer because future, none of the lightband technologies, none of that had any sort of deep insight into how a future failed. And that's a showstopper. When you ship async code, if something fails, you want to know how it failed and why, so you can fix it. And Zio came along and it shipped execution tracing, I think about 2 years ago in the first version. And we've improved it since then, improved performance. But what we wanted to do for Zio 2.0 is take this to the next level. And to take execution tracing to the next level, there were two things we had to do. Number one, make it faster. And number two, make the traces cleaner. And Rob's put a lot of time and effort, as well as several other people, in making execution tracing way cleaner to help you quickly diagnose problems and find the cause of the failure. So we know that Zio 1.0 execution traces can be a bit overwhelming, and we're working on cleaning that up and fixing that. But then the other performance problem in Zio 2.0, we're actually taking a radically different approach to execution tracing. And this approach relies on metaprogramming in Scala 3 and macros in Scala 2. And basically at compile time, we look and we see, oh, this line of code over here is calling into this Zio function, and we keep track of that. And because we're keeping track of that at compile time, it has virtually no performance impact. And then at runtime, we have even less to do than we've ever had to do before. So runtime execution tracing and stack tracing, there's almost no code. It's almost not doing anything interesting because all the heavy lifting is done at compile time by using Scala 3's advanced metaprogramming as well as Scala 2 macros. And what this means is that you can get the same great execution tracing and stack tracing that you've come to rely on from Zio, but you can do it at almost no performance cost. So this is almost cost-free execution and stack tracing, and that's mind-blowing. So current Zio code, almost everyone runs with execution and stack tracing turned on. In purely synthetic benchmarks, that has more than a 2 times impact on performance. So that means your code is running twice as slow as it could be running if you were willing to give up those features. Of course, no one wants to give them up. What this change is effectively doing is doubling the performance of your Zio applications in purely synthetic benchmarks. This might not translate into actual double performance because your application is doing lots of other things, not just Zio stuff, but nonetheless, it's, in my opinion, a game changer to achieve this sort of performance. And keep in mind, the same machinery is also powering profiling and other features. And this is unique to use of a concrete effect. So you're only going to see this performance benefit if you're not doing tagless final. However, we will have sort of a tagless final emulation mode. So if you still like programming in that style, you'll be able to get execution traces out of it, but it's not going to be as fast as the new stuff, which is powered by metaprogramming and macros. Another really important area where we wanted to push the boundary of what was possible is in metrics and monitoring. And that's because Zio has never been the effect system that leaves you right after you compile the code. We want to be with you after you compile the code and package it up and ship it off to production. We want to help you in that environment. So that's why we brought execution tracing to Zeo. That's why we're bringing profiling to Zeo 2.0. And that's why we're improving performance of execution tracing. And that's why we're adding built-in metrics into Zeo 2.0. So that means that when you plug in another library called ZMX into Zeo 2.0, you will automatically get the following types of information without having to do anything. You won't have to write a single line of code. You will get information on fiber lifetime. So how long are your fibers living? Also fiber failures. So when fibers die, how do they die? And you can see all of this information in real time as it's changing. You've got a problem with Java IO exception, or a problem with null pointer exception, or this exception or that exception. You can see that in real time, and you can plug that into whatever sort of monitoring tools you're using. And then you're going to see fiber count. So you can see fibers go up and down. And if you have a leak, you could see that on the graph, and all sorts of other things that you're going to get out of the box. And not only will you get all these amazing metrics out of the box without having to lift a finger, but ZMX also makes it trivial to plug in your own metrics. And you get all the same support that you do for the Zeo metrics. So with just a couple of lines of code anywhere scattered throughout your application, you'll be able to instrument them very, very easily in a high performant fashion that's fully integrated with the Zeo ecosystem. And we will support out of the box Datadog and StatsD and Prometheus and maybe New Relic as well. We're seeing about that one, but we'll support all of these different reporting backends out of the box. And then in addition, when you're developing this on your local machine, you'll be able to spin this up and take a look and see all these graphs without having to run any external service. So we'll just have sort of built-in functionality for purposes of development and testing. So all of this is coming. Almost all of this has been implemented already and is tested. It's going to be amazing. It's a real game changer. This is open source. So I know like Lightbend has sort of a commercial tool that gives you this functionality for the Lightbend stack, but this is 100% open source. You know, no one's trying to make any money off of any of this. We're just trying to get out in front of the community with sort of the best tooling we can possibly think of to help companies be successful deploying functional programming at scale. Another area where we're putting emphasis into is Zeo's support for low-level concurrency structures. Zeo 1.0 has a blazing fast ring buffer. That ring buffer, it's backed by an array, and it is the implementation of ZeoQ. So it's a low-level structure that has a higher level structure built on top. It's non-blocking, 100% async, and it's safe to cancel computation. So if you're trying to take something from a queue or offer something, you can time that out. And timing that out doesn't leak resources. So it has all the properties that you want of a high performance, async, safely cancelable queue. It's powered by this low level ring buffer structure that is blazing fast. How fast? Well, you can see how fast if you compare it with the highly optimized FS2 queue or the highly optimized Cats Effect 3 queue. It's substantially faster than either of those. Out of the box with the zero tweaking, it's just that much faster. However, there's a little bit of a problem, and that is a queue is not the best solution to every single problem in the world. Queues are great for distributing work. You have one or more producers, and they're all stuffing things in a queue, and then you have maybe a bunch of consumers, and then they're all taking things out of the queue. That is great. That's the perfect use case for a queue. But queues are not so great for broadcasting. Broadcasting scenarios occur all the time in streaming data applications. Sometimes you'll have one stream and you need to broadcast it to lots of consumers who all need the exact same information because they're going to do different things with it. That's essence of a modular streaming architecture, is the ability to do that fan out or the broadcast operation. And you don't really want to use a queue to back that, because then every consumer needs their own queue. And then when a producer produces an element, it needs to write that same element into every queue. You can already do that with ZeoQ, but it's just not very performant. And we knew we needed to design something that had the same caliber of ZeoQ, but that was designed for the broadcast scenario. And so Adam Fraser came along and implemented something that's built on a ring buffer as well. And it's called ZHub. And what ZHub gives us is the ability to basically write into a ring buffer, a bunch of producers, one or more producers write into a ring buffer, and all of the consumers read from that ring buffer. And then the slowest consumer sort of, actually there's lots of different strategies, but in the back pressure default strategy, when the slowest consumer reads from an element, then producers are allowed to write into it. That's how that works. Although there's other strategies like sliding and dropping and so forth that you can choose. This is super fast. Amazingly fast. How much faster? Well, take a look. So ZeoQ is really, really fast. If you use ZeoQ to implement the broadcast scenario, well, it's tremendously faster than FS2 topic or Cats Effect 3 queues for the same purpose. But it can't keep up with the hub. So the Z hub is, you could see 10 times as fast as the ZeoQ for this specific use case. So that's why it exists. We needed something like this. Now we have it. We have the Q, which is good for distribution, and the hub, which is good for broadcast. And the other one we might specialize, we'll see, is sort of a fan in. So fan out, fan in, and then just sort of horizontal. Those are the three main structures. We want to hit them all. We want Zeo to be your sort of one-stop shop for all the super fast, super low level, async, safely interruptible structures that you need to build modern applications. And then finally, one of the last things coming to Zeo 2.0 is a new basis for Zeo Streams. So Zeo Streams has existed for some time, but for a while, we've been looking for a different basis for it. And what I mean by basis is we're trying to discover some sort of almost mathematical essence of streaming. What does it mean for a streaming library to be compositional and complete? What does it have to have? What does it have to look like? What algebraic properties does it need to satisfy? How do you know when you have pieces that can solve all possible problems? And there are practical reasons for wanting this. It's not just the pursuit of something that's beautiful and mathematical. It's actually, there are practical reasons as well. I'll talk about one of them in a second. But we have experimented over the past year. We've experimented with, I want to say, probably 4 or 5 different bases for streams. And none of them have really clicked. Well, finally, after lots of research and experimentation, I've worked with Itamar and Dayon and Daniel and Balash and Adam and several other people to come up with a new basis for Zeo Streams, and that is a Z channel. A channel is a data type, just like in ordinary Java, that you can read and write. It can do reading and writing operations. It's the bundle of those two capabilities. It can read from upstream, and it can write to downstream. And you can imagine it as a channel of information, and you can compose 2 channels together. And there's lots of interesting ways you can compose and transform channels. But a channel, it's a low-level construct. It is a very imperative in feel. But it turns out, if you have a channel, you can implement Zeo Stream as well as Zeo Syncs. So both streams and syncs can be viewed as aspects of a unified whole. And in fact, with this particular modeling of streams and syncs, channel's all you need for everything. Everything can be done with channel. You don't need anything else. Streams and syncs are just specialized channels that offer higher level, more declarative semantics. That's amazing. It's amazing because previously Zeo Stream was its own thing with its own code base, and Zeo Sync was its own thing with its own code base. And then we had Zeo Transducer, which was its own thing with its own code base. And now we find out, oh, really? There's some deep hidden math here that says all of these things are aspects of something even more general purpose, which is the channel. There's really beautiful, a real beauty and elegance to this that's just amazing to behold. And not only that, it's not just, like I said, it's not just theoretical, but one of the great things that happens when everything is really a channel. Okay, so Zeo Streams 2.0, it's not going to look much different. It's going to be the same as you're already used to, but it's going to have a different basis, a different implementation. One of the great things to come out of that is that when you go to write a pipeline like this one here, which reads from an input stream and decodes the bytes into UTF-8 and splits the words and then counts all the words, so basically word count, in a few lines of code is that ultimately all of these things are operations on channels. So they're constructing channels, transforming channels, and composing channels. And as a result, a single channel interpreter or executor is responsible for executing the entire pipeline. And it can have advanced optimizations that can fuse different channels into one. It can do crazy advanced things in a way that's tractable. So we can actually implement these operations because we don't suffer from combinatorial explosion of possibilities, which has happened in some earlier encodings of Zio Stream. And what this means is that performance can be brought to new highs. So in Zio Streams 2.0, even without aggressive optimization, which of course we will do, we'll do aggressive optimization before this is ready for release. We're already looking at double the performance of Akka streams, which was the fastest solution on this particular CVS decoding benchmark. And this comes directly from the fact that all of these data types in Zio Streams 2.0 are merely manifestations of channel. And now we get to bonus topics. So what's coming to Zio 2.0 that we haven't talked about? Well, as you might guess, if you've been sort of paying attention to some of the presentations Adam has done and some of the buzz in the community, is that something called aspects are coming to Zio. So Zio Test has previously had aspects that allow you to do timing out of tests or running them parallel or accessing environment variables, running them only on the JVM and so forth. Aspects are enormously powerful. And what an aspect is basically a transformer. A Zio Test aspect transforms one spec to another spec. But aspects appear everywhere. Aspects appear in Caliban. They appear in Zio Query. They appear in Resiliency, which is a third-party Zio library. They appear everywhere. Everywhere you start looking for them, you start seeing them. And so what we're going to do in Zio 2.0 is bake them into Zio itself. So suddenly all these library authors who are independently inventing and building these things can now leverage machinery that's baked into Zio. An aspect is nothing more than a polymorphic function from effect to effect that allows you to modify the air or environment type in some way. And we'll be adding the syntax used in Zio Test directly to Zio, which is the @@, which suggests an annotation or sort of aspects from like aspect-oriented programming that allows you to tweak an effect in some way by applying an aspect to it. And then we'll be shipping Zio 2.0 with a bunch of different aspects such as timeout and bulkhead patterns, tracing and rate limiting and so forth. You know, I don't know if all of these will be in Zio or in how many will be in third-party libraries, but we'll definitely be shipping Zio with some of them, and then you'll be able to go and get the rest of them in third-party libraries. And that will enable you to do things like my effect, time it out, trace it, rate limit it, using that syntax. Or you can bundle up all of your aspects into one, and then just do @@ all aspects. This is going to give you a way to compositionally tweak and modify your effects in a standardized way, which is very important, I think, for scaling Zio to new applications. And then in other news, one of the things that we will be doing in Zio 2.0 is adding support for state. So some people have wondered, will Zio ever get more type parameters? It already has 3, but some people have wondered, what about state? Because if you've come from a Haskell background, you know there are things called reader, writer, state monads, and Zio has a reader baked in. Well, why doesn't it have state baked in? Why doesn't it have loggies, or why doesn't it have writer baked in? Why doesn't it have all these other things? It turns out that Zio never needs more than 3 type parameters, and the reason is those 3 are as powerful as you can possibly imagine. And that said, however, a lot of people run into the problem of how do I add state to my Zio? So rather than have everyone independently invent the same machinery, in Zio 2.0, we're going to bake this in the form of something very lightweight. It's only going to be a few lines of code. It's not going to take up a lot of stuff, but it's going to be there. It's going to be in Zio, and it's going to allow you to use state like you would a state monad, only without any of the drawbacks of state monad transformers and the performance impacts of like a state T that's actually trampoline is very computationally intensive and will slow down your base monad tremendously. You would never want to use that for performance sensitive code. Whereas the state stuff that's being baked into Zio is super fast because it's built on all of the Zio stuff and doesn't use any additional trampolining mechanisms, doesn't actually use state functions in order to do its magic. So you'll have operations like Zio update state and the ability to project out some state and the ability to set and get state directly on Zio. And of course, they'll just access information that's stored inside the environment in a fiber ref. So I won't explain exactly why that's there, but it gives you the same properties as a state monad, basically. So if you fork off a child fiber, it gets a copy of your state, but it can modify it independently, and you don't have to worry about those modifications being reflected in your parent fiber. All right, so beyond all of these amazing improvements coming to Zio 2.0, including the newly revamped microsite that will also be updated for Zio 2.0 and the cheat sheets and example projects, a lot of the really exciting things are happening not in Zio, but outside Zio. They're happening in HTTP and microservices. So things like, well, obviously people have been using HTTP4S for some time, but now there's Zio HTTP, which is a brand new, faster than Vertex, substantially faster than HTTP4S and Akka and so forth, library that's Zio native. In addition, there's Zio TLS HTTP, which is also very fast and Zio native. There's Uzi HTTP, which is Zio native. Zio Web is in development and is coming along very nicely. Tapier has really great support for Zio. Izumi has a whole microservice framework that works great with Zio and so forth. So we're seeing tremendous explosion in the ecosystem of Zio native solutions. And in persistence, you've been able to use Dubi for a long time. Now there's Zio Quill, which is great to see that. And it's able to take advantage. It feels more like a Zio native thing because it's taking advantage of the environment and doing things in a way that offers higher usability than the other effect systems can offer because they don't have the environment. And Zio SQL is operational right now with everything, I think, except insert queries for Postgres, and MySQL is coming along. Support for data is looking really great. Zio Kafka is very reliable, extensively used in production. Zio AWS, Daniel's done an amazing job creating and the entire AWS API in a Zio native package. Zio DynamoDB is in development, and that I am actually working with the author on that. I don't know when it will be announced, but that library there is auto parallelizes and auto batches stuff and has very high usability and will probably be implemented on top of Zio AWS ecosystem benefits. Zio Redis, that's an amazing library. It is going to be the best Redis client, I think, on the JVM. When it's done, it will be better than the stuff on Java. So super fast with support for the full range of Redis operators in transactional mode and non-transactional mode. It's just really, and custom sort of codecs and serialization as well, all baked in and super clean. These are amazing libraries, and they're going beyond the framework, the fabric that Zio gives you. They're reaching up all the way to the business problems that you face, and they're going to keep on going up there. You know, the higher we can bring functional programming, the more concrete, specific pains that we can solve, the more impact we can have, and the more successful we can make the Scala programming language, as well as the functional programming paradigm. And I think many of the libraries you see here, and many of the ones that I haven't talked about that are in development, some of which I'm working on, some of which I probably don't even know about yet. I see new libraries pop up, seems like every week, are going to make massive impact on the way that business writes software, because they're going to be, number one, doing FP. And that means giving you composition, giving you the ability to have superpowers when it comes to solving problems, as well as take advantage of the extraordinarily powerful Scala compiler that can help you identify bugs at compile time and fix them before they happen, before they ever ship, before you even write the unit test. But then beyond that, they're going to be pragmatic. They're going to be focused on ergonomics and usability. None of the theory stuff, none of the ivory tower academic stuff that's really hard to use and hard to teach. No, these next generation functional programming libraries, they are aggressive. They will tackle messy real world problems without fear. And they're not afraid to use familiar names, and they're not afraid to throw away type classes and implicits and type level programming and stuff that is useful, but is maybe going to be confusing. They're not afraid to make those compromises and to bring something that's very accessible, very user-friendly, very easy to teach, but still principled, still very principled, still built on the beauty of compositional, statically typed functional programming. They're going to bring all that into a package that I think is going to do wonders for commercial functional programming in Scala. Well, that's all I have for you. I hope you're excited about both why you should be using functional programming. This gives you a way to talk about why Zio. So if you're trying to bring Zio or Cats Effect or Monix into an organization, then look at that list, speak that language, show those examples. That will get you traction. Don't talk about the, oh, pure FP and side effects have to be wrapped and stuff like that. No, that's not solving problems people have. The problems I talked about in this presentation, they're problems everyone has. They're problems business have. And you show these compelling examples to someone and they're going to be like, yeah, maybe we can't afford to not use this. Maybe we hate functional programming, but this just looks too compelling for us to avoid. That's how you get FP into skeptical environments, is you don't talk about the FP so much, you talk about the benefits that this has on productivity, including the fearless refactoring that Girish mentioned earlier. These are compelling, they're super compelling. Focus on those, and that's going to help you. So hopefully you've gotten excited about that. Hopefully you have ammunition to bring a functional effect system into your place of work. If not now, then maybe next year. You know, several people a year ago were asking me, how do I convince people to use Zio? I said, wait a year, your colleagues will be trying to convince you to use Zio. And that's actually worked out in a number of cases. It's very exciting to see that. It's very exciting to see functional programming start to become mainstream in the Scala community. And I can foresee that growing. Like Girish mentioned, you know, this thing is not going to stay where it is today. There's just too much good software out there. There's too much good education. There's too many stellar teams forming. There's too many people who are helping other people learn. You know, things like the FP Bootcamp that Capital One has running. There's too much of that going on. This cannot be contained. This is a revolution in functional programming, and I'm super excited to be a part of that and to be helping people and to be watching it all happen inside the Scala community. So hopefully you're excited about Zio 2.0 as well. I think it's going to be a release that builds on what we did before. It's not going to be a major a rip and replace. It's going to be very super easy upgrade path, and it's just going to add polish and usability and performance. It's going to make the good stuff better and fix the little bit of bad stuff that we had, the usability issues we had around ZLayer and a few other things. It's just going to be more of the good stuff and less the bad stuff. So I would encourage you to give Capital One a try if you're looking for a new job and you want a company that will invest into you and also believes in functional Scala. Then give them a try. They seem to be a great firm to work with, and I'm happy that we're partnering with them and that several Ziverge employees are working to help make Capital One successful. Also, you can check out Ziverge.com if you want to apply to our company for a position, or check out our course catalog, many of which we're running. You can follow me on Twitter, LinkedIn, and GitHub at JDGoes, and you can learn more about Zio and Zio Dev. I also do mentoring one-on-one on Patreon if that's something you're interested in. All right, so now I'm going to open it up for questions. I saw a bunch of questions earlier on I didn't have the chance to answer. Let's see here. Question from Shishira. How much of performance overhead would the Zeo Fibers add to execution while they are expanding and contracting stack frame? That operation is super efficient. It's actually implemented with arrays that have 13 elements in them. And as the stack grows to the 13 element size, basically a new array is allocated and stored in one of those elements. And that's fast. That's about as fast as you can make a stack. It's faster than ArrayList and so forth. and it allows the stack to grow and shrink over time. I would say no overhead, no significant overhead. Kurt asks, without threads, are exception call stacks still useful, or do you find other ways to add context to failures? So the exception call stacks are not super useful. We save them in any case, but the main way in which we add context to failures is by every time you call flat map. Basically, flat maps are, okay, we're going to do this, and then we're going to do this, and then we're going to do this, and so forth. Every time you call a function, there'll be a flat map in there. So we reconstruct what is the analog of a stack trace by looking at the flat maps. That's how we do the stack trace in Zio. And then in addition, to give you even more context, we have the execution trace. The execution trace is just a linear log of operations. So you can see userland code went from here to here to here. It entered this if statement, it went here. It's like a log, really, but you don't have to pay the cost of writing that log. The execution trace is almost too detailed. It has too much information. It can be a bit overwhelming. So it's up to us to make that information easier to digest. There's no scarcity of information, though. And actually, I didn't mention this today, but in Zio 2.0, the quality of that information is improving tremendously because we had to go to great lengths to maintain quality information using the older approach for execution tracing. The newer approach does not require as much maintenance, and so it's easier to get that right. So the quality that I've seen from new execution tracing is way higher. There's much less information on the guts of Zio than there is in the older one. Yes, the boss is kind of micromanaging. Yeah, I suppose that would be an engineering manager, the kind who used to code and can't quite give it up, something like that. Frank says, can't wait to see Zeonomicon updated with this new Zio 2.0 layer stuff. Yes, that's going to be great to go back and update that documentation and teach people the simpler ways of building layers that we've gradually discovered. Stephen asks, can compositionality be extended to distributed systems? Yes, yes, it can be. And so one of the most exciting technologies in development in the Zio ecosystem, I think, this is my personal opinion, obviously, what's exciting depends on what's interesting to you. But one of the things I work on a lot with one of our developers, Ash, is Zio Flow. Zio Flow is bringing to distributed computing Zio's ideas about compositionality. And it's going to give you persistent distributed computation. So imagine if you could just express some sort of complicated workflow that involves calling this API and that API and sleeping for 2 days and then interacting with a human and getting them to do something. Who knows? Or it could just be a bunch of microservice calls giving you transactional guarantees across parts of those, as well as persistence. So if the node that's executing one of these workflows goes down, then that computation is just transferred to another node executing in the cluster and resumes where it left off. This is giving you the ability to solve incredibly hard problems, like just mind-bogglingly complex problems in a simple way. With just a few lines of code, you don't have to worry about failures. You can program in a model of computation where the machine never goes down. That's amazing. You don't have to think about persistence. This opens up the door to solve problems that people currently spend. They spend huge development budgets and lots of engineers writing lots of code in order to solve these types of problems. Solutions to those problems will become accessible to solo developers by using a technology like Zio Flow. I think if you're interested in distributed computing, keep an eye on Zio Flow because it's going to be a highlight of the Zio ecosystem. Stephen asks, I imagine the Zio runtime is pretty tricky under the hood. Yes, it is. As someone who has spent the last few years away from Scala, only watching from a distance, can you say how proven solid the runtime is? I'd say it's very proven. First off, Zio does not rely on property-based tests and algebraic laws. It has a massive catalog of handwritten unit tests that only ever is added to. We continuously add new tests all the time. That's growing all the time. The very few times we haven't encountered any problems in months, probably, almost a year, I would say, before any user reported bugs. And even then, they weren't that serious. But nonetheless, anytime we do encounter a bug, we add regression tests to make sure that that will never happen again. And also, I'm very passionate about keeping that runtime system small, because the smaller it is, the easier it is to reason about. And so over time, I've gotten good at doing more with fewer lines of code and writing it in a cleaner way, and also using the sort of microkernel-based approach for Zeo's runtime system, where parts of Zeo's runtime system are actually written in Zio itself, which means you can be way more productive. So I feel very confident about the quality of that code, and I work in it a lot. In my opinion, the code quality there has improved, as well as the number of tests have improved over time. And it's been proven in production, I would say, for the past year. And even though parts of it are undergoing upgrades, it has the same bones as the existing one. The Zio 2.0 runtime system will have the same bones as the existing one, but it will be even smaller and even simpler than the 1.0 version, with even more unit tests. Yeah, parts of there are functional code. It's a hybrid, and that enables it to be a microkernel. So to have a microkernel design requires that you implement parts of the Zio runtime system in Zio itself. That's why Zio's runtime system is 1,000 lines of code, and if you look at other ones, they're 10,000 lines of code. Or maybe not 10,000, but at least 3,000. It could be as many as 10,000, depending on which one you look at. And it's because Zio is trying to, be as compositional and almost fractal as it can be, to squeeze the amount of code down to something very small that you can get your head around. Steven says, with STM, it becomes even more important to keep code purely functional because code could be reevaluated. How is it possible to detect violations of purity in Scala? I recall that wart remover helps. What tools do you recommend? Wart remover can detect some types of things. There's a project called Zio Shield that made some efforts to detect impurity. You could also set up a Scala fix to catch common calls of side effecting methods. And I know Martin Odersky wants to do some work adding pure function types to Scala. I don't know when that would happen. It would not be until, like, I don't know, 3.3.2 or 3.3. But if that ever happened, then you would have the compilers help to enforce that. Nathan asks, how do you compose error types from different domains? And that's a good question. So in Scala 2.x, Zio will automatically compose error types according to least upper bound. And that means that if you're creating your own error hierarchies, then one of the options you have available to you, thanks to Scala's support for subtyping, is take sealed traits and extend domains that will be composed together. That allows you to use the sort of automatic least upper bound composition to unify different error types into one, and do that in a type safe way. That's, according to FP best practices, because as sealed trait, it becomes an algebraic data type. You can pattern match against it. It could either be this error or this error or this error. So some people use that technique. A lot of people just say, oh, I'm going to make all my errors extend exception. So if I have two totally incompatible errors and I compose these effects together, I end up with exception. I no longer know which one it is, but at least it's good up to that point in time. Other people take one error and embed it in another error. In Scala 3, Zio will support union types for error composition. So if you compose something that fails with E1 and something that fails with E2, then you'll get back something that fails with E1 or E2. And that's really nice, because you don't need to modify the inheritance hierarchies. You don't need to manually embed one error in another. You don't need to otherwise convert one error into another. It's just something you would get for free. Fadi asks, when is Zio 2.0 going to be released? So we're targeting the July, August, early August timeframe, 1 year in between major releases. All right, let me quickly check on Discord, see if there's any other questions. Hopefully we're going to have a milestone release in the next 2 weeks or so We still got more stuff to merge in. We have all these branches and we've got to get them all merged into master. It's coming along though quite nicely. We did an experiment with S coverage. We don't currently use that. The comparable to Akka cluster would be Zeo flow. So Frank asks a good question, which is, what are the advantages of Zeo streams over Akka streams? And I would say the advantage is, first off, you get all the other advantages that comes with Zeo software. So automatic, pervasive interruption, resource safety, compositional timeouts, context, you get the environment everywhere so you can plug things in without having to rewire your application. You get all those benefits that come from just using Zeo. But a bigger point is that Zeo Streams is built on FP and built on structure and algebraic structure. Like my whole spiel about Z channel being a really great foundation for Zeo Streams. Well, it turns out that basically all you really need in a streaming library are two data types. You need a producer of values, that's a stream, and you need a consumer of values, that's a sink. And then you actually build a whole pipeline by connecting the two. But then you need ways to compose two streams, and ways to compose two sinks, and ways to transform a stream, and ways to transform a sink. And that's all you need. That's really all you need. The entire class of streaming applications can be solved with those two things and nothing else. That's amazing because you as a programmer can now master two data types, and suddenly you've mastered the entire category of streaming applications. Contrast that with Akka streams. Akka streams has lots of data types, not just two, more like 20, or if you really count them all, probably 40. And in order to master Akka streams, you need to know about all of them and how they interact and which ones are used for which other purposes. It's way more complicated. And at the end of the day, could you say for sure that you would be able to solve all problems using combinations of these 20 not so composable data types? Probably, I don't know, maybe. But there's nothing sort of essential or fundamental or mathematical about Akka streams. Whereas with Zeo streams, there is something essential. This is the nature of streaming. This is when you peek back the curtain, this is what you see streams are actually made of. They're made of these pieces, and these pieces fit together in these certain ways. And these ways allow you to solve the entire class of streaming problems in a very compositional, small, compact package that you can reason about. And once you master these two things, you know how to solve problems in that category. One more from Frank, and then I'll wrap it up for the evening. You mentioned Zeo and Scala 3. Can you elaborate on that? And how does Zeo take advantage of Scala 3? So a lot of things in Zeo are already, so Zeo was the first major library to compile on Scala 3. And we've been working with a Scala 3 compiler team on a lot of issues over time, not just in Zeo, but also Zeo Flow and related applications. And we're trying to make all Zeo libraries compile and ship on Scala 3 and have really first-class support for Scala 3. But a lot of Zeo features were designed forward-looking to Scala 3. And that means if we saw something was going to be supported in Scala 3 in a really nice fashion, we would just sort of go all in on it, even if it didn't quite fit in Scala 2. An example of that is error composition. So least upper bound for error composition is not ideal, but in Scala 3, it can be union types. So there are other things like that where things get easier and more natural and more elegant and more beautiful and more powerful in Scala 3 that are already there. Now, that said, there are a few areas where we think we can do something in a different way that's going to be a lot better for people by taking advantage of Scala 3 specific features, but people will be using Scala 2 for a long time. So what we're going to have to do for Zeo 2 is have separate Scala 3 only methods and so forth that can only be called in the Scala 3 code base that won't exist on the 2.0 stuff. And maybe even a separate data type or two that is only designed for Scala 3. And then we'll have to, still most people will be using the Scala 2 one for the next couple of years, but the goal should be, if there's something you want to play around with, use that Scala 3 package. And then at some point in the future, I'm not sure when, it could be Zeo 3.0 or maybe not, maybe Zeo 4.0, but at some point there, actually it probably would be Zeo 3. I can't say for sure though. Zeo would itself be sort of native, have all of these Scala 3 features. We would be tweaking the design to expect to work with Scala 3 and then only supporting the Scala sort of maybe 2.13 in a more legacy note. Now that's way out, so you shouldn't worry about that now. But the point is, like, we are plugged into what's happening with Scala 3. I teach Scala 3. I've helped work with the Scala 3 compiler team, getting Zeo issues solved. So we are thinking about that. Zeo is already great at supporting Scala 3, and it's only going to get better over time. Even though if you're stuck on 2, don't worry, because Scala or Zeo on Scala 2 will be supported for a very long time to come. How does Zeo 2 relate to Prelude? They don't. So Zeo Prelude is a different project, and you'll never have to use Zeo Prelude to use Zeo. They're just two totally different things. Zeo Prelude is for people who want a library like Scala Z or CATS, but done in a more modern way. So Zeo Prelude doesn't use any Haskellisms and tries to embrace covariance and contravariance and work well with the Scala collections and so forth. So it's designed to be basically a better Scala Z or CATS that has no Haskellisms, and it's thoroughly well integrated into both the object-oriented as well as the functional aspects of the Scala programming language.